Thanks a lot. And also thanks to the audience for being here on a Sunday morning, first session after Saturday evening. You must be really interested in the talk. So thanks. Yeah, the title is quite long, so I'm not going to repeat it, but basically want to show you how we built up a complete end-to-end environment infrastructure for basically picking up a model and solving one of our business problems. And the agenda for today will be that we give you a brief introduction about the company, the product, and the problem. Then we look at the overall system, how it looks on a high level. Then we go into specifics and look into one part as data engineering, another part is the model training, last part is the model serving, and then we wrap it up with a summary. Okay, let's jump into the introduction. So briefly about the company, it's basically a financial technology service company. It's founded by Eduardo Villar, who's a serial entrepreneur and actuary from his educational background. We have basically award-winning products, and they found some traction over there in Silicon Valley, and hence we could basically attract venture capital money from some well-known funds over there, and also some leading members of PayPal. And basically, why are we here? Because headquarters in San Francisco, but we have a big engineering office in Madrid, where we all, the three of us, are based. So that's briefly about the company. But now let's talk about one thing that is in the e-commerce space. There's a huge inefficiency around return transactions. So imagine you're a shopper, you buy something at Decathlon online, and it takes you approximately 5 to 8 business days until it arrives at your place. And these numbers are all US numbers. We're looking at the US market. So once you received it and you're not happy with one of the items, you basically initiate a return. From there, we see basically that it takes 3 to 5 days until people actually bring it to the post and send it back. From there, it takes again 5 to 8 business days until it's back at the warehouse of the merchant. There it takes again 3 to 5 days until a refund is actually issued. But that's not the moment when the money is on your bank account again. It takes another 3 to 5 days until you have it on your bank account again. And then maybe because quite some time passed by, you're going to repurchase, but that's very likely at that point of time. So basically we're talking about 21 days where your money is basically frozen and you can't do anything with it. That's a large inefficiency if you think about it. So how is Returnly solving for this inefficiency, for this problem? You again place your initial purchase, and again 5 to 8 days, and you decide that the product is not what you were looking for, and that's basically the point of time where you initiate your return. And at that point of time, we look basically whether we want to take that risk and give you a credit so that you can basically repurchase with that amount of money. Hence, what we see, yeah, that once you receive that instant credit, we see that in 90% of the cases people go and repurchase the same day. And meanwhile, it takes again 3 to 5 days in parallel that the shopper goes and sends the item back. And but in parallel, basically your repurchase is being delivered to you. So basically, we see customer loyalty increase. We see customer satisfaction also go up. And from there on, everything else goes behind the scenes for the shopper. We basically are in touch with the merchant and take care about settlement and all of that. So what we see is we dramatically reduce the time the shopper needs to wait until the money is back and is able to repurchase. That's basically our value proposition out there to overcome this inefficiency in the sphere of e-commerce return transactions. And our main product for this is called machine learned underwriting. Let's decompose this term and look actually what underwriting means. The definition of underwriting is that you sign or accept a liability under an insurance policy to guarantee payment in case of loss or damage. What is the liability in this case? It's a credit that we issue to the shopper. A loss could be if the returned item is never sent back to the merchant, because yeah, that's basically a complete loss. And a damage would be if somebody is picking an item, tries it, does whatever, and sends it back damaged. And that's basically and if you want to then basically model it mathematically, that would be the definition, but it's, in a nutshell, it's a classification problem. So, sorry. Apologies. So why end-to-end? And you saw it surely in the title. We see basically in many large organizations that the org structure is you have data science in one bucket, where data scientists do model training, offline batch scoring, offline evaluation, and then you have another department, engineers, who actually build software and ship software. And this has obviously some benefits, but also some challenges. Sorry. And the challenges are that sometimes the departments are not strategically aligned, and that engineers and data scientists don't speak the same language. Maybe there are some friction in the communication, and engineer doesn't understand what the data scientist needs, and the data scientist vice versa doesn't understand what the engineer needs to know. And what we found for ourselves a very useful approach is so-called full stack data scientist. What does it mean, basically? We want to be able to end-to-end own a piece of software, and we understand our models as a piece of software. So hence we are looking basically for T-shaped individuals. We get to that term in a second, but what that means is basically we look for a certain breadth, that you have general knowledge in data, working with data, math, and coding, but then you have basically also one specific area where you go in devs. And sorry. And so if you look at the skill sets for one individual, he has this this breadth and all this area that we are looking for, but then goes in one specific area like Bayesian modeling and devs. And if we then continue this exercise and look at all the team members, what we end up with is a team that covers basically the full range that we need, basically ship software end to end, consisting of models, but also we go really deep in terms of the areas and things that we can cover. And not surprisingly, our day-to-day work looks more like software engineers. We do a lot of software design, coding, dry principles, testing, documentation. And with that, I'm already over time.
Okay, I'm going to start with the system overview. What requirements do we have in our company? In terms of modeling, we need generalization, we need good predictions in the future. Also, we need experiment tracking to evaluate all the experiments we do. We need model selection. We have a problem of cold start, because if we have a new shopper or a new merchant, we have to do really high quality prediction for them as well. Also, in terms of software engineering, in our team, we have code versioning, we do pull requests, we do reviews. If you develop something and you have to merge to master, another member of the team has to approve that pull request. Also, we have unit testing for what we develop, and we have continuous integration for deployment. We're going to explain that later. In terms of architecture, we have a microservice that needs to have a low latency API, because it's a real-time application. And in terms of this doesn't work very well. In terms of analytics, we have real-time tracking. We measure real-time metrics, and also we have dashboards. We do reporting. Okay, then. Then, what is our architecture? A global view of our architecture, okay? We have a transactional data. We have transactional data for each order, each return, and everything. Then we have an analytical database that we have this information aggregated, and we use for analytics. Also, we have a different batch preprocessing jobs, and we persist this information in a feature store and an S3 bucket. I'm going to explain what it is later in detail. And what are our main two repositories? We have MLU Trainer and MLU Predictor Service. MLU Trainer is the repository we use for training and for experiment, okay? We track the experiments with MLflow. MLflow is a Python package, okay? And we have MLU Predictor Service, that is where we have the API, and we have the service that we use to make the predictions. Okay, Then let's go to the data engineering in depth. Okay, what kind of data we have? Okay, we have these different entities. We have orders, we have returns, we have repurchases. Also, we have merchants and shoppers. But this information, we need different kind of aggregation for each of them. Okay, we characterize somehow the merchant and the shopper with aggregated information. I'm going to explain it, but it's more about the last 3 months. The last 2 months is aggregated information, but in terms of orders, repurchases, and returns, we use the transactional data, okay? And how we need this information is different because at prediction time, we need disaggregated information about merchants and shoppers, and we need the returns, but at prediction time, we need orders and repurchases. It's different how we need the information. Okay, what is our pipeline in detail? As I said before, we have this transactional database. We aggregate this information, and then we have the analytical database. Then this batch preprocessing job, we use a Spark to take advantage of the parallelism, to be flexible. And essentially, there are different complex queries, and we save these features that are in the feature store. The feature store, what it is? It's a Redis key value database, high performance that we need at prediction time because we need the speed. Okay, and we have an S3 bucket when we have the data sets for training. These are the two different ones. And for example, to be more concrete, imagine that you have these entities, okay? And we have these complex queries. This is about the feature store, okay? We have these entities. We aggregate the information we aggregate this information with jobs, with different jobs, and we create features like total orders in the last 90 days for a shopper, total unique shoppers in the last 90 days for a merchant. And this information is saved in the feature store because at prediction time, we need this information very fast. We cannot calculate this at prediction time because it's going to increase the latency of our problem. Then these features are in this feature store, and we access very fast with this using Redis, okay? These are two different dimensions. Okay, then I'm going to go with the model training. First, I'm going to explain a global view about machine learning. It's going to be very fast. How we see machine learning is okay. What is a model? A model is a representation of reality. We have simple and complex models, okay? What are the pros and cons? Simple models are easier to interpret, and we need interpretation if in our problem. We need to understand what are the main drivers of our predictions. Also, complex models tend to perform better, only in complex problems to be, okay? And we have, if the model is simple, the latency is lower, okay? It makes sense. And also the training time is lower if the model is simple. And if the training time is less, we have less training time, we can do more experiments at the same time, you know? We can try different things faster. And in terms of optimization, you have a function to minimize. This function can be your business function, or it can be a different one. The closer is to the business function, the better. But sometimes you minimize the log loss, but you are actually maximizing the revenue. Then you use different algorithms for different models, like gradient descent for logistic regression. And sometimes heuristic techniques are enough, because you are looking for a good enough solution. You don't need the global minima. With a local minima, it's fine. Then how you split the data? We divide in train, validation, and test set. Why? This test set, we don't use it until the very end, because it's the good proxy, it's the better proxy you can have to know what is going to be your performance in production. And also, if you have this time dimension, you only use the past to predict the future, to be unbiased, okay? Then the bias-variance trade-off, a few points is like the normal pitfall is to use the best model to choose the best model that applies to the overfits the training data. Okay, that's the common pitfall. What we do is we select the best model in the validation set. Okay, and we evaluate the real future performance with the test set. Then, if you look at this graph, you would choose the model with less validation error. It doesn't matter actually the training error, because we're looking for generalization in the future. And that's all.
Okay. Then, so a key part for achieving generalization are hyperparameters. What are hyperparameters? If during training, what we are actually learning are the parameters of the model, hyperparameters explain how the model is defined and how the algorithm is going to learn from data. And this is a key process for improving performance out of sample data, because it's going to help us navigate this bias variance trade-off that Pablo just talked about. So this is going to help us improve our performance out of sample. Also for us, it's very important to have this process of hyperparameter tuning automatic, because as they have said, we see machine learning a little bit like software engineering. So we don't want to do this process manually. We want to actually use some techniques that allow us to have automatic hyperparameter tuning. At its core, hyperparameter optimization, it is just a kind of global optimization. And this would be, what do you want to maximize? You want to maximize the, let's say, the outsample performance. So you use the cross-validation score as a black box function of your hyperparameters, and you are trying to find a maximum in this space. Then there are several ways of doing this. There are some naive approaches. So all kind of general optimization techniques can be used for this. But these simple naive approaches are probably the most used. You have grid search, that is scikit-learn, and random search. In grid search, basically you use a brute force global optimization algorithm, so you explore in a structured way the different combinations of hyperparameters. And then with random search, you actually are just sampling from your hyperparameter space in a random fashion and evaluating your loss function and seeing if you are reaching a good point. Then there are more smarter ways of doing this, and I think there have been already several talks about this. But we use Bayesian global optimization, and actually we use the package Hyperopt that uses the tree structure parsing estimator algorithm. I'm not going to go into the details because we don't have time. But if you want to know more, please you can ask us afterwards. And then I really like too the Gaussian process approach, so Gaussian process-based optimization, and there is also a package called BaseOpt in Python that you can use for that. Okay, and this is the core package for training. Of course, well, this hyperparameter optimization is a core part of our training package, but this is a little bit like the structure and the different technologies that we are using. We do the ETL from the history bucket, where we have our master data set that we use for training. And then we do some quality assurance, some QA using pandas, basically pandas. And then this would be like the core of our model, how our model is built. We use scikit-learn pipelines in order to concatenate the different transformations and have like the full machine learning model in a single Python object, which is quite handy. And then we leverage the whole scikit-learn stack, basically. So we input missing values, we use sentinel columns to indicate, like in a binary variable, where the missing values are. Then we use one-hot encoding. So we have a full pre-processing pipeline built with scikit-learn that is a little bit adapted to the different kind of features that we have. We have feature selection, then we use imbalance learn to do under and over sampling, and then we have the final classification where we have model selection and the hyperparameter tuning. We do all this hyperparameter tuning for the whole pipeline, so not only the main algorithm, the main parameters of the algorithm, but the main pipeline, and then we use PyTest for testing and MLflow for experiment tracking, that we will talk more about that later. Then this is the main object that we use, is the scikit-learn pipeline. And it's very handy because, as I said, you can concatenate the transformations of scikit-learn in a single Python object, and you give the .fit, .predict signature. You can do the full hyperparameter tuning, and you minimize the cost of going from training to inference, so it's quite handy. The cons that it can get quite complex, and the metadata extraction can be cumbersome sometimes. For doing this, you just have to define the transformations, and then you use the make pipeline function to concatenate them. Then Hyperopt, as we said, is the tool that we use. And it's quite simple, really, because it's a black box optimization algorithm, so you need to define an objective function that takes as parameters the hyperparameters that you are going to test. You rebuild the model, so in this case, the whole pipeline, using a function to create the model object, and then you define the cross-validation, and you use the cross-validation score as the output of the black box function. You can define a search space with actually probability distributions that help the optimizer to sample from this search space, and then basically you can use the fmin function to find the best trial. So you make several trials and you find the best one. This is a little bit just a snapshot of our full pre-processing pipeline. We leverage to the column transformer of scikit-learn that is very handy to do different transformations to different kind of features. And then just you can explore, for example, something that you can do that is very interesting is exploring the different trials of the optimization algorithm. You can build another, let's say, machine learning model on top, and then you can get the feature importance. So you can see what are the hyperparameters that affect the most your performance, which is always like a quite interesting exercise.
Yeah, we mentioned initially that we apply a lot of dry principles. So most of you should be familiar with dry principles in software development, and why we thought why not apply it to modeling as well. So we have a lot of kind of boilerplate code that we reuse for hyperparameter optimization, and we said also that basically model interpretability is crucial for us. So what we did is we created one abstract base class called model optimizer base, where everything is basically either implemented or interfaces are defined that then need to be implemented by the specific implementations. And then here we have, for example, one elastic net optimizer, a decision tree optimizer, random forest optimizer, and so on and so forth. So we found this to be really useful for our purpose. And yeah, it's basically an interface for all the model optimizer classes, and you can adapt it for high-level parameters like what feature processing to apply, what feature selection technique to choose from, sampling strategies, classification model. You can pick different kind of models, cross-validation, and so on. And what needs to be implemented? You need to basically specify a dictionary, a search space, what hyperparameters to basically search, and from what distribution to sample from. You need a factory method, make model, that basically creates this scikit-learn pipeline object. And then you need another factory method called metadata extractor that basically that needs to be implemented by us. So the moment we call this function, we get a function that extracts the metadata of that specific model. That is really important for us when we have issues, and we are able to go into the model and see basically what is the model metadata, what are the coefficient terms, so that we have an understanding of the model. And what is already implemented is optimized hyperparameter, so we don't need to reinvent the wheel there. And here we see basically a bit of the implementation. Optimized hyperparameters is all done. You just need to implement basically metadata extractor, make model, and the search space dictionary. And yeah, we mentioned that we use MLflow. It's an open source package for a lot of different things, but we use it primarily for experiment tracking. And it's super easy to use. You basically define an experiment, and then you have methods for logging parameters, metrics, or artifacts. We store, for example, the model artifacts. We log some parameters like a decision threshold, and also iteratively, programmatically, we log all relevant metrics, both machine learning and also financial metrics. Here you see a screenshot of the UI, but not going to talk in detail about that. And with that, let us go over to model serving, because that's the other crucial element of the MLU. It's not really about training, but really about how can this be deployed and be used in a real-time setting. Don't worry about basically the overall flow, but the important part is basically that we have one key element in this big machinery, and all the requirements that apply to the rest of this kind of piece of software also apply to us. So we can't basically live in a ignore these, but we also have to make sure that everything is tested, everything works fine, everything works with a low latency. Otherwise, that leads to a poor user experience, just like now. Okay, I think the slide is broken, but let's talk about how deployment takes place. We have a CI pipeline implemented in BuildKite for both production and development environments. We every time something is committed or a pull request being created, we run more than 50 unit and integration tests. Also, code quality checks are run automatically with Pylint. And so here we see basically the master branch and a development branch, not a specific one. So the moment we want to make a change, we branch from the master branch, and those changes can be either a retrained model, a new model, other changes, bug fixes, security fixes. Once those changes are done and reviewed, we make a commit to the development branch, automatic execution of a pilot, test, and then basically deployment to dev environment. From there, a pull request, a colleague reviews everything, and then again, lint, test, and deploy to production. And with that, we basically made sure that we don't have any big disaster scenarios. We also, because it's basically production code, we need to make sure that we are able to real-time track what's happening. So we use Prometheus and Grafana for this purpose. Not gonna talk too much about it. It's basically open source and also very easy to implement. And with that, we can go over to the summary and speak about what the achievements are. We basically picked a model and replaced a set of manual business rules where you have to basically go and see if this happens, then that. And so we found that our solution is better suited for this purpose. We saw that it has a significant financial impact. We verified this with running A/B tests, randomized split tests. We obviously had some challenges, and what we see basically, one of the big challenges is model degradation. Why is this happening for us? We are basically a startup. We have high growth. Our merchants also have high growth rates, and basically transactions happening today on our platform are not going to be the same basically happening in 2 or 3 months down the road. So what we need to do is frequent retraining and deployment of the models. I mentioned this now a couple of times, but latency is really an issue. So we are constantly working on keeping latency low. It's an ongoing thing. And what we also figured out is a bit difficult is unit testing for machine learning code. You always have non-deterministic pieces and elements in it, and it's a bit challenging at times. We haven't found a definite solution for it, but we found some good starting points, and we're still keeping us busy with this area. And at the beginning, when the team was very small, time zone difference was a challenge. So we ended up in occasions having to wait a full day until the colleagues in San Francisco were up and were able to approve the pull request. With now the team in Madrid growing and then being bigger, this is not a challenge anymore. And what did we learn out of all this? We basically figured out there are no one-size-fits-all approaches. There's no free lunch. There are no easy solutions. And this applies to basically both our code base, but also to figuring out which tool or which package or library to use for the job. And we have the approach of identifying the right tool for the right job. And with that, so far, we made good experience. Another lesson learned is basically we're touching production system, and it's a danger zone. So we need to be really disciplined. We need to be systematic. We need to have attention to detail. Be at times a bit annoying towards our colleagues in the pull requests, and we across the bench figured out that Python for this purpose, for implementing and shipping and deploying MLU, was for us the best decision to make. It's really a great programming language. The ecosystem is really rich. So for us, it was the best decision to go with Python. We obviously also have future work. We are interested in automatic deployment with fast rollback. So we're looking into things like blue-green deployment. These are some interesting venues we would like to pursue. We want to do automatic retraining and model selection. Right now we do manual retraining, and we sit together, we discuss as a team which model out of 20 runs, for example, to pick from for the next deployment. We want to choose more complex models. We have right now fairly simple models implemented, but they are good enough. But we obviously are interested to also evaluate more complex models. And what we as a team can't emphasize enough is to identify and make more features available. I think features are basically the foundation for even for more complex models. And with that, just want to make a quick announcement that we are also hiring. So we are looking for both machine learning engineers and data scientists. If you're interested, shoot me an email or come afterwards and talk to us. And with that, we open up for questions. Thank you all.
Well, thanks for the talk. I have one question regarding the latency. You're using MLflow for like the serving layer, right? When you're doing real-time inference. I wanted to know some numbers, if you would do some numbers in terms of like each request is 50 milliseconds or something like that.
So the question was about latency and whether we use MLflow for model serving. Yeah. No, we don't use MLflow. We just use it for experiment tracking. Model serving is basically the predictor service that we implemented ourselves, and we started somewhere around 40 milliseconds, and we are right now around 80 milliseconds. So the moment we
Flask or Starlet something.
Exactly, yeah.
That was the slide that was broken. That was the slide that was broken, the Flask slide. The Flask slide it wasn't working, yes. That was the problem, yes.
Hello, yep. I have two questions. First is, I don't know, you mentioned, how do you solve the cold start issue with new clients, new customers, because the model has to be training all data and perhaps you don't have it all, or the merchant doesn't have it. And how do if you have thought about the filtering issue that happens when I understand that when you apply these models, then when a user requests a returns an item, then you can deny the money to the user if your model says that this user is probably going to return the item damage or never return it. But then if you do that, after some time, perhaps you find out the model reinforces itself, because every time you deny always to the same users, later the historical data you will have will be affected by this. So have you thought about how to solve this? Do you have a control group where you apply this, or?
Yeah, this is a very good question. We are aware of this kind of echo chamber effect and reinforcement loops. So what we do is basically we always make sure that we have data completely randomized running on a platform, and that we use that for collecting training data. So we are fully aware of this issue, and we want to make sure that we don't have it 100% deployed, so that we collect training data. So for this, does that answer the question? Yeah. Okay. Oh, the cold start, yeah. That's we basically have two cold start problems. One is the merchant cold start, and the other one is the shopper cold start problem. In both cases, we use imputation to fill up missing features, but we figured out that one case is worse than the other one, and our model basically is being trained with imputation, and we figure out if we pick a new shopper, we have at least some portion of features initially, but the rest is basically imputed, and our model is still able to make predictions, and the performance is good. Yeah, so we solve for this that way.
Hello. Maybe I lost it, but maybe you can help me to clarify something. How do you keep traceability of the full pipeline so you can reproduce the experiments in the future, some experiments you did in the past? So keep reproducibility of the experiments on all the versions of your model. How do you keep track of that in the full pipeline?
Yeah. Do you want to? Okay. Yeah, the question was around reproducibility. How do we make sure that the whole pipeline can be reproduced? And yeah, there are obviously some non-deterministic parts of it. In many cases, you can define a seed. So we make sure that this seed is basically set manually. And what we do is we don't just train it once, each model. We train it a bunch of times. So even with the same hyperparameter settings, we just train it multiple times with an increment of the seed number, and then we look at mean and standard deviation for all the kind of metrics that we are interested in. And by simply fixing those seeds and then incrementing them, we make sure that it's reproducible.
There is time for one more question. If I may, just a doubt, in case of shopping holidays like Christmas or Black Friday, do you need to change the model, or it will adapt?
Yeah, that's also a very interesting question. That's an ongoing research topic about contextual information like that. And what we see in industry happening is that people have on-off switches for different models, one for kind of exactly for those circumstances. We are not there yet. We try to basically retrain often and cover things, but there are different settings where you might want to have different models for different kind of purposes, but we are not there.
We may thank again the professor.